should be live. Let me know if you can hear me okay. We'll share this stream on LinkedIn as well. Hopefully someone is able to join in. Well, someone already joined in. We'll be reviewing this paper quickly. Obviously not ourselves, using AI. We actually had some tools that will take a PDF and extract the text and the images, separate them into individual files. Yeah, so we have the extracted images, we have the paper itself, we have the extracted text, and then we also have the data. So we'll be hopefully getting into the weeds on this one. Yes, we have the images. Yeah, interesting. The first images. Yeah, the images are not in order because image 2 is figure 1. Whatever, doesn't matter. We got that. Yeah, we're using ChatGPT 4.0 in this case. Yes, we do have, before you ask, yes, we do have access to all the other models. But we will start with 4.0. We also have GitHub Copilot. I don't know, do you reckon another model will be doing a better overview? Well, probably O1 is the better model these days, isn't it? This from GitHub Copilot. We also have access to Claude 3.5 Sonnet thinking model and O3 Mini. This one has, well, does it have O1? Yeah, it has O1 as well. So that's pretty good. Okay, everything we do eventually appears on this website, so go check it out. Let me know what you think. We also, let's actually use one of our own tools for speech to text. Speech to text, this one here. We'll actually place it in another window. Yeah, it's making a lot of mistakes. It's not great, but it's our own, and we want to test it and improve it, so we'll be using that. Okay, let's do O1. Can you give a summary of the paper the main drawbacks from it. And a summary of the whole conversation that we had, but just in general terms, don't go prompt by prompt, just overview of the whole thing. Whole thing. And let's try O1. And let's read what we've got so far.
Here's an overview of the study by Jiang Li et al., titled Epileptic Seizure Detection Using Heart Rate Variability from Ambulatory ECG, a Pseudoperspectives 25, Journal of Neural Engineering. Objective: to develop and validate a patient-independent machine learning model for detecting epileptic seizures using heart rate variability, HRV, from ambulatory ECG recordings, rather than the conventional EEG data in real-world out-of-hospital settings. Methodology: data, long-term ambulatory ECG, EEG recordings from 65 patients diagnosed with epilepsy, 47 used for training validation via leave one patient out cross-validation, 18 held out for prospective testing. Model, logistic regression using features derived from RR intervals, HRV such as cardiac sympathetic index, CSI, and modified CSI. Labels, seizure-related periods, perictal 2 minutes before to 2 minutes after seizure versus non-seizure periods, interictal. Evaluation, event-based detection using sensitivity, specificity, and improvement over chance, IOC, Tashley AUC, with realistic rules for windowing and detection. Holdout test set, 18 patients. 18 patients showed better than chance performance. Mean sensitivity, 72%. Mean specificity, 68%. Performance was significantly better in patients with focal epilepsy, patients who were responders. Average HR increase more than 50 BPM during seizures. Significance: demonstrates that seizure detection via ECG is feasible in ambulatory settings, a shift away from hospital-based EEG monitoring. Offers a non-invasive, comfortable, and wearable compatible solution for long-term seizure tracking. Introduces a pseudo-prospective evaluation framework reflecting real-world use more accurately than retrospective methods. Limitations: not suitable for real-time alerts due to detection latency. Performance variability between patients, not all benefit equally, e.g. non-responders. Further work needed to reduce false positives and apply to wrist-worn devices or more diverse populations. Conclusion: this study offers a promising proof of concept for ECG-based seizure detection in the wild. While not perfect, the approach is a step toward practical, wearable, continuous seizure monitoring, especially for patients where EEG is not viable.
Okay, so we get the general overview. Obviously, it's being highly positive about it, but yeah, so we're asking if the paper is actually claiming to be able to find seizures from ECG alone. And want to know how well it can do it, if at all.
Yes, the paper explicitly claims it can detect seizures using only ECG data, specifically heart rate variability, HRV, features derived from ambulatory ECG recordings. Claim: we developed a patient-independent, machine learning-based seizure detector using ambulatory long-term ECG monitoring data. ECG data was the only input used for seizure detection.
How well does it work?
Overall performance, holdout test set, 18 patients. Sensitivity, 72% proportion of seizures correctly detected. Specificity, 68% proportion of non-seizure time correctly labeled. Better than chance detection for 78% of patients, 1418. Best performance observed in focal epilepsy patients versus generalized. Responders, patients whose heart rate increased 50 BPM during seizures. Threshold adjusted performance, when high sensitivity is prioritized. Sensitivity, 81%. Specificity drops to 54%. When low false positives are prioritized, high specificity, 80%. Sensitivity drops to 55%. This shows the model can be tuned depending on clinical needs, e.g., minimizing false alarms versus maximizing seizure detection. How early can it detect seizures? Detection isn't real-time or early warning. Instead, the model detects seizures by analyzing periictal periods. Periictal window equals 2 minutes before to 2 minutes after seizure onset. This window is labeled as positive for training and detection. So the model can detect within a 4-minute window centered on the seizure and sometimes before the seizure begins, but this is not guaranteed or consistent. Seizure-induced autonomic changes may occur at different points during the periictal period, rather than aligning perfectly with annotated seizure labels. Key limitation: this system is not for real-time alerts or early intervention. This seizure detector is not suitable for real-time seizure alarms or detection that requires low latency or precise detection timing. Section limitations. It's designed to help clinicians assess seizure burden over time, e.g. during home monitoring, not to warn patients before or during seizures. TLDR, yes, the model detects seizures using just ECG. It achieves 72% sensitivity in unseen patients. Detection happens within a periictal window, 2 minutes from seizure onset. It's not a real-time or predictive tool, but useful for long-term seizure tracking. Want a visual breakdown of how the detection window works or how performance varies by seizure type?
Okay, there's actually, well, yeah, so obviously 72% sensitivity is not great. But yeah, especially with specificity is actually much lower. It's around 60, 65, whatever, 68, whatever, something percentage. 68, yeah. Interesting enough, so detection happens within the pre-ictal window. Well then, yeah, plus minus 2 minutes from seizure onset. So if it's plus, it's not pre-ictal. How is it plus minus? Plus minus. Did I say it in the text? Before. Yeah, they do say it in the text. Defined as 2 minutes, and it's in figure. It's in this figure there. Is it pre-ictal? It's meant to be like post-ictal? I don't. Is that the definition? Is that the definition? I don't know enough about it, even though I should. But yeah, it's the naming conventions. Yeah, so that's 2 minutes there. So it's 2 minutes before, after seizure. Onset. Onset will be the beginning. Yeah, it's confusing. It's confusing. Can you clarify this? Can you also give clear definitions? Well, we know what a seizure is. We know what onset. Onset will be the beginning of the seizure. You can confirm that. Then pre-ictal, by the name of it, it sounds like whatever is happening before seizure onset. Does that make sense? Because that's not how it was used in the paper. Can you look up the titles from the paper and tell me if it's okay? Should we do it with O1? Yeah, probably. Use the best model for that because that's important. Yeah, I don't know why can it not be real time. Like, how long does it take to process the data? we actually have the data so we can see how long does it take. The data though is not raw, which we do not like. We will go into it later on. So asking, do authors claim that the ECG can replace EEG with sensitivity of 72% and specificity of 68%? Well, luckily, supposedly, no, they don't claim that.
Great question, and you're picking up on an important nuance. No, the authors do not claim that ECG can replace EEG. Instead, they position their ECG-based seizure detection system as a complementary tool, especially in situations where EEG is not practical or available, such as long-term ambulatory at-home monitoring, when continuous EEG is uncomfortable, obtrusive, or not feasible. For patients who cannot or do not wish to undergo invasive EEG procedures, what they actually say. While implanted EEG systems provide better signal quality, the devices and medical procedures are not suitable for all patients. Seizure detection via identifying induced autonomic changes utilizing ECG wearables can provide a more impartial method of tracking seizures on an ongoing basis to complement or refine seizure diaries. This seizure detector is not suitable for real-time seizure alarms or detection that requires low latency or precise detection timing. Purpose of their ECG-based detector, it's designed for retrospective seizure tracking, not as a diagnostic replacement for EEG. The 72% sensitivity and 68% specificity are considered proof of concept levels, good enough for monitoring trends over time, but not for diagnostic use on their own. The authors specifically emphasize realistic performance expectations. Many patients won't show clear heart rate changes during seizures. ECG signals are indirect markers of seizure activity compared to EEG, which directly captures neural events. Bottom line. The authors are careful not to overclaim. They don't say ECG replaces EEG. Instead, they suggest ECG adds value in home-based seizure tracking, can reduce reliance on subjective seizure diaries, and could serve as a supplementary signal in wearable long-term monitoring systems.
Okay, so the authors do claim that it can reduce reliance on subjective seizure diaries. There's always this thing about like bashing patients for not being able to record their seizures properly, which is, yeah, I keep hearing it over and over again. And same as with data like this, it is not conclusive. Obviously, some patients will be able to do it much better than others, especially if your seizures are not affecting your memory or anything. You will be able to, if you're fairly organized. But it's nothing to do with reduce. Why are we trying to reduce reliance on seizure diaries? I mean, if they're working, if they work, they work. It's just one of the, I would say, highly significant tools. But yes, obviously, as engineers, we are biased because this is something the patients can do themselves and they don't need our help. Yes, you can create like an automated a seizure diary, like a digital seizure diary. Maybe you can use AI for the language processing of like describing a seizure and things like that. But other than that, there is nothing to monetize on in the industry of seizure diaries, because it's just, well, pen and paper or digital notebook. Okay, so then we're asking, is EEG necessary by definition to diagnose epileptic seizures? Why does the paper review ECG alone? because to actually confirm false positives, false negatives like they do, they must have recorded EEG at the same time, because that's the gold standard. The way you diagnose epilepsy, you have to have EEG, but then the EEG is not available in the dataset, and so I'm not sure how the labeling was done. Was the labeling based on seizure diaries, or did they have the EEG recording going on at the same time? I don't know if they answered this in the discussion somewhere of the paper. That would be good to know. Yes, so the other thing is ECG is normally, yes, recorded during normal EEG recordings in epilepsy patients. So I want to know if the paper addressing any of that.
You're asking incredibly insightful questions. These go right to the heart of epilepsy diagnosis and the paper's motivation. Let's unpack each one clearly. Is EEG necessary by definition to diagnose epileptic seizures? Yes, in clinical practice, EEG is typically considered necessary or at least standard for a definitive diagnosis of epilepsy, particularly to confirm seizure types, identify epileptiform activity, spikes, sharp waves, localize seizure onset zones. EEG directly records electrical activity in the brain, making it the gold standard for diagnosing epilepsy. However, EEG isn't always available, especially in long-term real-world settings. Seizure activity may not occur during brief EEG recordings. Some patients' seizures may not be associated with detectable EEG changes. So while EEG is standard, some diagnoses are made clinically based on behaviors, witness reports, etc., when EEG isn't possible. 2. Why does this paper focus on ECG alone? The authors explain this clearly. Scalp EEG systems are difficult to maintain and prone to signal interference in active and noisy recording environments. The devices can be uncomfortable for continuous wear and are often obtrusive and highly visible, which are disliked by patients, leading to low long-term adherence. They argue that ECG is less invasive, better tolerated for long-term home-based use, widely available in consumer wearables like chest straps, smartwatches. The goal is not to replace EEG for diagnosis, but to support long-term seizure tracking and help complement or replace seizure diaries, which are often unreliable. Is ECG normally recorded during EEG recordings in epilepsy patients, and why? Yes, in modern epilepsy monitoring units, EMUs, ECG is routinely recorded alongside EEG. Why? To monitor for autonomic changes during seizures like ictal tachycardia or bradycardia, to help detect potentially life-threatening events like SUDEP, sudden unexpected death in epilepsy, to support seizure classification, certain seizure types, e.g. temporal lobe epilepsy, are associated with heart rate changes, to supplement EEG when EEG data is unclear or inconclusive. The paper also notes this. It is widely recognized that seizures can alter autonomic functions by affecting the cortical limbic areas, section introduction. ECG signals have been employed to detect seizures as an independent or complementary data source to EEG. Yes, the paper explicitly addresses all these points. A. Why ECG only? ECG monitoring systems are less prone to noise and better tolerated by patients in long-term use. Our study demonstrated that ECG data is useful for long-term seizure detection beyond in-hospital monitoring. B. They don't claim ECG replaces EEG. This seizure detector is not suitable for real-time seizure alarms or detection that requires low latency or precise detection timing. Section, where EEG is unavailable, it can complement other diagnostic approaches. Summary.
Okay, there's one question about the wearables being used, like they mentioned chest straps and smartwatches. Now the question is if heart rate enough, or do you need a continuous ECG recording like some devices can record? Okay, I'll just give a quick summary for the paper. I might be looking at the data as well, but yeah, I'm just trying to get a few details first.
Summary of the paper by Lee et al. 2025. Goal: demonstrate that seizures can be detected from ambulatory ECG alone by looking at heart rate variability, HRV. Method: a machine learning model, logistic regression, was trained on ECG recordings from 47 epilepsy patients and evaluated on 18 additional patients. ECG-based HRV features like cardiac sympathetic index were extracted, and seizures were labeled in a perictal window around each event. Key results: overall sensitivity on new patients by 72%, overall specificity 68%, better than chance performance in most patients, 78% had positive improvement over chance, stronger results for focal epilepsy or patients with large heart rate surges, responders. Main drawbacks, limitations: 1. Not a replacement for EEG. The authors do not claim ECG alone can fully replace EEG for diagnosing epilepsy. EEG remains the standard. 2. No real-time alarms. This system is designed for retrospective seizure counting rather than immediate alerts. 3. Variability between patients. Some show weak heart rate changes, so the method can miss those seizures. 4. Ambulatory noise and false positives. Normal daily activities also raise heart rate, causing false alarms. High-level overview of our conversation. We discussed that the paper uses only ECG for seizure detection rather than EEG, achieving moderate sensitivity and specificity. We clarified it's not a direct substitute for EEG, which is still the gold standard. We reviewed how ECG is commonly included in clinical EEG setups to monitor heart rate changes, e.g. for SUDEP risk. We covered the paper's pseudo-prospective method, its performance, the advantages, comfort, continuous wearable usage, and its limitations, not real-time, not fully replacing EEG. Essentially, the conversation centers around how the author's ECG-based method fits into epilepsy care. It's a complementary or alternative approach for long-term seizure tracking at home, but not a formal EEG replacement.
Yeah, interestingly enough, for this long prompt, one thought for a whopping 27 seconds in machine time. That's like a year. Let's actually read that quickly, because it's actually interesting to know how is it reasoning, what's its way of thinking is.
The user is confused about naming conventions for periods relative to seizure onset, especially the terms periictal, praectal, and postictal, questioning the 4-minute window description in the paper. The user seeks a clearer understanding of periictal, ictal, and praectal definitions, especially in relation to the 4-minute window surrounding seizure onset, and asks for consistent alignment with the paper's terminology. The user's confusion arises from the paper defining periictal as 2 minutes before and after seizure onset, while praectal typically refers to the period before seizure onset. The user is searching for the exact definition in the paper, which describes the periictal period as the time from 2 minutes before to 2 minutes after seizure onset. The text specifies the periictal period spans 2 minutes before to 2 minutes after seizure offset, combining overlapping segments into one event. The periictal period spans 2 minutes before and after seizure onset, as illustrated by the seizure period's duration in the study's time series data. The periictal period spans from 2 minutes before seizure onset to 2 minutes after seizure offset, as depicted in the figure in the text approach snippet. The periictal period spans from 2 minutes before to 2 minutes after seizure onset. Data outside this range is labeled as interictal, aligning with the defined time frame. The periictal period spans from 2 minutes before to 2 minutes after seizure onset. This includes the seizure event and aligns with the training data's time frame. The peak period includes 2 minutes before onset, the entire seizure, and extends 2 minutes after offset, while ictus spans from onset to offset. The periictal period spans 2 minutes before electrographic seizure onset until 2 minutes after onset, defining the interval for labeling the positive class. I'm piecing together that the model was trained on data from the periictal period, spanning 2 minutes before onset to 2 minutes after onset, or possibly 2 minutes after offset. I'm rethinking the typical periictal period, which commonly includes 2 minutes before onset to 2 minutes after offset, for more precise model training. Okay, let me see. The model's training involves the periictal period, encompassing 2 minutes before seizure onset to 2 minutes after offset, plus the seizure itself, totaling 4+ minutes. The model's periictal period spans 2 minutes before seizure onset to 2 minutes after offset, covering the seizure itself and extending 4+ minutes beyond. This timeline is pivotal for accurate analysis. Pulling together info on periictal periods, 2 minutes before seizure onset to 2 minutes after offset. This interval includes the seizure itself, crucial for precise labeling and analysis. I'm mapping out distinct timeframes. Ictal spans onset to offset, praectal precedes onset, postictal follows offset, and periictal envelops the entire seizure, including 2 minutes before and after. Okay, let me see. To thoroughly label the periictal period, covering everything 2 minutes before and after the seizure helps capture the complete seizure window. Interestingly enough, the periictal period spans 2 minutes before seizure onset to 2 minutes after offset. This window aligns with the author's definition to ensure precise labeling.
I don't know. Yeah, I got confused with periictal. I thought it just says preictal. Because traditionally you have preictal, ictal, postictal, interictal. So I'm not sure why is it different in here. Also, it is a bit confusing. So we have a seizure, then we have 2 minutes before and after. So the periictal is taking the whole time, including the seizure. So have they tried the different a type of analysis, or they just did the periictal? I guess if the time is exactly specified, yeah, we essentially want to know what the definition for false alarm and false negative and false positive were. That's pretty important. Okay, let's actually read the response quickly.
Below is a straightforward clarification of how Ellie et al. 2025 defined periictal versus preictal, ictal, and postictal, and what exactly 2 minutes before after the seizure onset means in their paper. NAR 1. Standard clinical definitions. Seizure onset, the moment time zero when electrographic EEG or clinical signs of a seizure begin. Seizure offset, the moment the EEG or clinical signs return to baseline. Acictal period, from seizure onset to seizure offset. Preictal, any period before the seizure onset. Postictal, any period after the seizure offset. Periictal, broadly, the time around the seizure. Authors often define this to include the seizure itself, ictal plus some buffer before and or after. 2. How this paper defines periictal. In figure 2b of the paper, they explicitly say, the periictal period, blue, is defined as the time from 2 minutes before seizure onset to 2 minutes after seizure offset, encompassing the seizure event, red. So practically, 1, if a seizure starts at t equals 0 and ends at t equal plus 60 seconds, 1 minute. 2, their periictal period label for that seizure would be from t equal minus 120 seconds to minus 2 minutes up to t equal plus 180 seconds plus 2 minutes after offset. Hence, this yields a 4-minute buffer, 2 min before onset plus 2 min after offset surrounding the actual seizure. All data within that span is labeled positive or periictal for training and evaluation. Everything else is negative, interictal. 3. Why people get confused. The paper's text sometimes summarizes the periictal window as 2 minutes from seizure onset, but the figure and the more complete passages clarify it is 2 minutes before onset until 2 minutes after offset. This can be misunderstood as if they only used -2 to +2 minutes around the onset itself, but they actually extend the window beyond the offset. So to confirm, 1, onset equals when the seizure begins. 2, the paper's periictal, onset -2 minutes through, offset +2 minutes. 4, preictal versus periictal. If you read preictal, you typically think before the seizure, but the authors are labeling any data from 2 minutes before onset all the way to 2 minutes after offset as periictal. So periictal in their study includes the true preictal phase, the 2 minutes before onset, the ictal phase, the seizure itself, the early postictal phase, up to 2 minutes after offset. Scherner 5. Why not just the seizure itself? The authors explain that they need a bigger window because heart rate changes may start before the formal EEG onset. Some autonomic changes can lead in. Heart rate changes may persist after the seizure ends, postictal dysregulation. Using a bigger window also provides more training data for the machine learning model, and it reduces the mismatch between exact EEG labeled onset and real-life physiological changes that might not align perfectly with EEG markers. Bottom line, in this paper, periictal is not simply preictal. It's the entire window from 2 minutes before the EEG-defined onset through 2 minutes after the seizure offset. That's how they label all those samples as positive for their model.
I'm working through the confusion, clarifying the benefit of automated detection and the speed of data processing, all while considering the applicability of instant access to process data. Pondering the integration of technology versus diaries, acknowledging the partial reliance on diaries while questioning the ability of ECG alone to replace EEG. An automated system can enhance diary accuracy and compliance, capturing subclinical or forgotten seizures, unlike traditional diaries, which may miss these events due to human limitations. Actively blending developments with business insights, I'm crafting advanced solutions that emphasize refined measures for more robust results. This encourages strategic investments and exploring new opportunities.
Below is a high-level reflection on why seizure diaries are often considered insufficient by clinicians and researchers, and why some form of automated detection, like ECG or EEG-based methods, is still pursued, even if patient-reported diaries can be accurate in certain cases. 1. Diaries can be very helpful for some patients. Certain people with epilepsy do keep diligent and consistent diaries. If their seizures are easily felt or remembered,
Diaries can be very helpful for some patients. Certain people with epilepsy do keep diligent and consistent diaries. If their seizures are easily felt or remembered, diaries can capture the majority of events. In these cases, diaries can help track patterns and guide treatment changes quite effectively.
They have a question. When they trained the model, they split it in a very specific way. Patients, there's 18 patients in test dataset. And another 47 patients in the training dataset. So I'm not sure why the specific split. We could ignore them or pull them together.
Why diaries often prove inaccurate, memory gaps, or impaired awareness. Many seizures, especially focal impaired awareness, your generalized tonic-clonic events with postictal confusion, may not be recalled accurately. Nighttime seizures. People can sleep through seizures or forget them upon waking. Fatigue and busy schedules. Day-to-day life can make it hard to keep a perfect log. Subjectivity. Patients may sometimes over-report or under-report based on how they perceive seizure significance or how motivated they are to note them. A wealth of clinical studies shows that diaries often miss anywhere from 30% to 80% of seizures, depending on seizure type and patient factors. Why researchers explore automated detection objective, continuous monitoring. Machines, ECG-based systems, run 24/7, so they don't rely on patient memory. Capturing subclinical events. Some seizures have little to no outward signs, but can still be physiologically measurable via EEG, ECG, or other biosensors. Medication optimization. A more accurate seizure count can guide better treatment adjustments, reducing patient burden, especially for chronic conditions. It's less stressful if a wearable device logs events than constantly writing them down. Why ECG instead of EEG? Wearability and comfort. ECG patches or chest straps are simpler than continuous scalp EEG. Long-term home use. EEG electrodes are more prone to signal loss and discomfort over many days. ECG is more stable if the patient is moving around or sleeping at home. Though less direct, ECG only reflects autonomic changes, like heart rate spikes, so accuracy varies person to person. That's why the paper's sensitivity is around 72%, not 90 to 100%. Why ECG instead of EEG? Wearability and comfort. ECG patches or chest straps are simpler than continuous scalp EEG. Long-term home use. EEG electrodes are more prone to signal loss and discomfort over many days. ECG is more stable if the patient is moving around or sleeping at home. Though less direct, ECG only reflects autonomic changes, like heart rate spikes, so accuracy varies person to person. That's why the paper sensitivity is around 72%, not 90 to 100%. They're not saying ECG replaces diaries entirely. The paper does mention it can reduce reliance on seizure diaries because objective data is typically more reliable. That doesn't mean diaries have no value. Many clinicians combine diaries plus automated detection to get a fuller picture. Nor do they claim it replaces EEG diagnosis. Diagnosing epilepsy still usually requires EEG evidence.
Yeah, we obviously, as you can imagine, using this new OpenAI text-to-speech. Can actually embed it in JavaScript. The input can be, can you use this to read any website? I mean, that's obviously until they take it down, because you're obviously using the OpenAI API. Would be an interesting project. Well, so far we can just yeah, we saved. Yeah, we saved the JavaScript. We might turn it. We'll need a HTML for it. I wonder if it can do entire conversations. I mean, eventually they will be integrating it into the speech, current speech model one day.
Why not real time? The author's method processes 50 to 100 second ECG windows, plus features like cardiac sympathetic index. They also combine or window data in multi-minute chunks to reduce false positives. This means detection lags behind the actual start of a seizure, so it's not meant for immediate intervention alerts. It's aimed at retrospective analysis to track total seizure burden over days, weeks, especially where diaries might be incomplete. Bottom line diaries work well for some patients, but not everyone. Automated detection, ECG, EEG, or multimodal aims to fill the gaps in self-reporting. The paper's 72%, 68% sensitivity specificity isn't perfect, but it's enough to improve average seizure tracking beyond diaries alone, especially for those who miss a lot of events. No one claims it's a direct replacement for EEG or that diaries are useless. Rather, they're complementary tools to get a more accurate seizure count and potentially better clinical outcomes.
We need a different different voice for a robot cheerleader, mad scientist.
Kasut was asking, is each necessary by definition to diagnosis?
Okay, KK. Let's just try a friendly one.
Kasut was asking, is each necessary by definition to diagnosis? Why does the paper review ECG? Hello. Because to actually convene for this false negatives like this, 2, they must have recorded EEG and the same time. Because that's the gold standard, the way you diagnose epilepsy. You have to have, but then they eat is not available in the dataset. And it's not sure how they labeling was done. Was the labeling based on seizure diaries? Or did they have recording going on at the same time? I don't know if they answer this in the discussion, somewhere of the paper. That will be good to know.
Okay, obviously there's a problem with the speech to text. This does text to speech. So we'll have like essentially 3 voices, one my own potentially. We could do one for the reasoning bit.
Trying to figure out how the labeling was done using seizure diaries or video EEG monitoring, because this is crucial for accurate diagnoses. I noticed the study used home-based video EEG with ECG for 65 patients. Professionals annotated seizures using EEG and video, while ECG data was classified separately. Okay, let's see. The study confirms seizures were labeled using EEG recordings. Ensuring precise identification via the established gold standard method by neurologists.
Yeah, that's fine. I don't know why it's talking like that, but it's something in the prompt for the speech. Let's go back to the original voice quickly.
How were seizures labeled? The paper states they used long-term ambulatory video EEG ECG studies from Seer Medical Australia. Each recording system had 21 scalp EEG electrodes plus 3 ECG leads, plus video capturing the patient at home. Board-certified neurologists annotated the start and end times of each seizure, relying primarily on EEG, the gold standard, combined with video review. Video and EEG data were used by the neurologists to annotate seizure times. ECG data was the only input used for seizure detection. Section, Dataset and Introduction. So no, they did not label seizures based on diaries. They had synchronous EEG and video to confirm the seizure events, then extracted only the EEG signal to develop and test the algorithm.
Is EEG necessary for diagnosis? Yes, typically. In clinical practice, EEG is indeed the standard for diagnosing epilepsy because it captures direct neural activity, seizure discharges, spikes. In this study, they performed video EEG as part of a standard ambulatory diagnostic workup. That's how they verified patients truly had epileptic seizures. Once the EEG-based labels were established, the ECG portion was used to see if an algorithm could detect those same seizures autonomously. Why focus on ECG alone then? Their core research question: can we detect seizures from ECG, heart rate variability, in an ambulatory setting without needing EEG? In real life, continuous EEG is hard to maintain for very long periods. ECG wearables are much easier to use 24/7 at home, so they tested how well an ECG-only method might work compared to the ground truth from simultaneous EEG.
I'm breaking down the differences between devices like smartwatches and chest straps. I'm curious about whether heart rate alone suffices or if continuous ECG is necessary for precise data. Clinically, continuous ECG is crucial for accurate HRV due to sophisticated features reliant on precise RR intervals. PPG-based devices provide approximate RR intervals, which might lack accuracy. While consumer devices provide useful heart rate data, advanced HRV features necessitate continuous ECG with precise R peaks for comprehensive analysis, surpassing the capabilities of sporadic measurements. It's becoming clear that relying on just heart rate is insufficient. For reliable HRV-based detection, continuous ECG or precise beat-to-beat intervals are essential.
Okay, they actually are doing a precise beat to beat, like a peak to peak measurement, supposedly.
HRV features depend on precise beat-to-beat RR intervals. The authors rely on heart rate variability HRV measures like cardiac sympathetic index CSI and Lorenz plots, which require precise, continuous RR intervals, milliseconds resolution. Averaged or intermittent heart rate data, like 1 reading per minute, won't let you compute these advanced features reliably. Noise and artifact rejection. Continuous ECG allows rigorous noise filtering and removal of artifactual beats. With just sporadic heart rate estimates, you can't always confirm which readings are contaminated by motion or poor contact. Ictal autonomic changes may emerge in subtle beat-to-beat patterns. Some seizure-related changes show up as transient shifts in HRV, not just a big jump in beats per minute. You need the full ECG waveform or, at minimum, a continuous
Did it time me out or something?
noise and artifact rejection. Continuous ECG allows rigorous noise filtering and removal of artifactual beats. With just sporadic heart rate estimates, you can't always confirm which readings are contaminated by motion or poor contact. Ictal autonomic changes may emerge in subtle beat-to-beat patterns. Some seizure-related changes show up as transient shifts in HRV, not just a big jump in beats per minute. You need the full ECG waveform, or at minimum, a continuous ECG, accurate RR series to detect these subtle autonomic dynamics.
Okay, we don't have the complete ECG. That should be, well, that's what we have, so.
What about chest straps and smartwatches? Chest straps. Many sport-oriented straps, Polar, Garmin, etc., do measure ECG from the chest wall. They can provide continuous beat-to-beat intervals, RR data, at a decent sampling rate. In principle, that's similar to the single or dual lead ECG the authors used. If the data quality is high, you could potentially compute the same HRV features. Smartwatches, PPG-based. Most consumer smartwatches track heart rate via optical PPG, photoplethysmography, not actual ECG. They can estimate RR intervals, but it's typically more susceptible to motion artifacts, especially during daily activity. Some advanced watches, e.g. Apple Watch ECG feature, can record short ECG snapshots on demand, but not typically a continuous ECG for hours/days. So, you might still miss key data or have lower fidelity for advanced HRV analysis. Data sampling frequency and quality. The author's approach relies on windowed HRV analyses, 50/E. Some advanced watches, e.g. Apple Watch ECG feature, can record short ECG snapshots on demand, but not typically a continuous ECG for hours/days. So, you might still miss key data or have lower fidelity for advanced HRV analysis. Data sampling frequency and quality. The author's approach relies on windowed HRV analyses, 50 to 100 second window. The author's approach relies on windowed HRV analyses, 50 to 100 second windows with 1 second steps. So you need a near real-time, high-quality RR feed. A random or low-frequency heart rate readout once every 5 seconds or 1 minute probably won't capture enough detail. 3. Can plain heart rate alone work? Merely having the average beats per minute every so often might catch big spikes, example, tachycardia. But it won't capture finer HRV changes that the paper leverages. You risk more false positives, example, exercise, stress, and more false negatives, small but distinctive HRV shifts. Hence, the paper's method is heavily reliant on continuous, accurately measured RR intervals, derived directly from ECG signals. I'm thinking through how the paper tackles false positives in heart rate from daily activities by using techniques like Lorenz plots and event detection with thresholds and consecutive samples. This helps avoid confusion with seizures. It's interesting to see how cross-validation ensures robustness. Incorporating multi-sensor approaches and advanced nonlinear HRV features aims to improve seizure detection and reduce false positives further. how the paper addresses false positives using advanced heart rate variability, HRV features. The authors don't rely purely on raw heart rate, which easily spikes during exercise or stress. Instead, they compute nonlinear HRV features such as the Cardiac Sympathetic Index, CSI, and Lorenz plot-based metrics. These features are meant to distinguish true seizure-induced changes, which may show specific signature patterns. From general autonomic arousal or normal activity, multi-window event detection rules. They apply a window-based decision. Each 50 to 100 second ECG window yields a feature set, passed to a logistic regression. Then, consecutive positive windows, 6 in a 5-minute block, for example, must occur to classify a single event as a seizure. This requirement of multiple consecutive positive samples helps filter out brief spikes from normal activities that typically last only a short while in HRV signals. Patient-independent, large data training by T.
Finish reading and didn't finish reading the whole thing, did it?
Multi-window event detection rules. They apply a window-based decision. Each 50 to 100 second ECG window yields a feature set, passed to a logistic regression. Then, consecutive positive windows, 6 being a 5-minute block, for example, must occur to classify a single event as a seizure. This requirement of multiple consecutive positive samples helps filter out brief spikes from normal activities that typically last only a short while in HRV signals. Patient-independent, large data training. By training on long-tail, patient-independent, large data training. By training on long-term ambulatory data from dozens of patients, the model sees a wide variety of everyday HR fluctuations and learns, to a degree, that not all tachycardia-like episodes are seizures. Choosing thresholds to balance sensitivity specificity. The paper explicitly discusses selecting detection thresholds for different clinical use cases. Some may want fewer false positives, higher specificity. Others want higher sensitivity. Tuning this threshold can mitigate false positives caused by normal daily HR elevations. Double windowing dealt with situations where the positive samples occurred across the edges of two adjacent detection windows. The strictness of the detection criteria, number of positively classified samples, helps avoid classifying short bursts of autonomic changes as seizures. Adapted from section, Event Detection. How it should be addressed. Further integrate multi-sensor data, motion, EMG, etc. Movement sensors, like accelerometers, can help differentiate activity-induced heart rate changes from seizure-induced changes. This is a common suggestion. If the algorithm sees heart rate rise plus intense movement, it may categorize it as exercise stress rather than a seizure. Refined algorithms. More context-aware models. Future machine learning or deep learning approaches might combine HRV plus wearable data, for example, respiration, skin conductance, to further reduce false positives from purely sympathetic arousal. Patient-specific adaptation. In some patients, exercise heart rates look very similar to their seizure heart rates. A patient-specific calibration could A patient-specific calibration could help the model learn each individual's normal daily patterns and set more personalized detection thresholds, longer or more detailed observation windows. By incorporating longer ECG history or additional short-term versus long-term HRV features, the model may better tell the difference between short-duration exercise spikes and more complex, lasting autonomic dysregulations linked to seizures. Key takeaway: in Lee et al., 2025. The main strategies to handle daily activity false positives are using advanced, nonlinear HRV metrics rather than mere heart rate, enforcing multiple consecutive positive samples in an event window, and optimizing decision thresholds for different use cases. They acknowledge there is room to improve by adding multimodal signals or more patient-specific approaches, which could further reduce false positives from everyday heart rate elevations.
I'm examining definitions like false alarms, false positives, and false negatives, particularly in the context of periictal and preictal, to elucidate their distinctions and implications. I'm rethinking event detection using Perkins metrics, periictal segments as true positives, interictal ones as true negatives, and overlaps as false positives or negatives, based on specific criteria. I'm honing in on a 5-minute event detection window, categorizing periods as periictal or not, and evaluating overlapping and non-overlapping periods for accurate true and false positives and negatives.
Below is a concise clarification of how Lee et al. 2025 defined their periictal window and how false alarms, false positives, false negatives, and true positives are determined. This should resolve the confusion about how they incorporate the seizure itself, plus 2 minutes on either side. 1. Periictal definition in this paper. Seizure onset. The neurologist marked start time from EEG and video. Seizure offset. The neurologist marked end time. Periictal period from 2 minutes before the seizure onset until 2 minutes after the seizure offset. This means each seizure's periictal label includes the actual ictal phase, seizure itself, the preictal, the 2 minutes before onset, the postictal, the 2 minutes after offset. All data in this interval is labeled as positive for classifier training and evaluation. Everything else is labeled negative or interictal. 2. Why they chose a wider window. Seizure-related autonomic changes can start before the formal. Two, why they chose a wider window. Seizure-related autonomic changes can start before the formal EEG onset, preictal, and persist beyond seizure offset, postictal. They want to capture any ECG heart rate variability changes that might be relevant, rather than restricting to the exact ictal period only. 3. Event detection versus sample by sample. They don't just classify each second or each short window on its own. They do event detection in 5-minute blocks or a chosen window size, looking for consecutive positives in the subwindows. Then they ask, does this 5-minute detected event overlap with a periictal label? If yes, true positive, TP. If no, false positive, FP, also called a false alarm. If there is a periictal segment with no overlapping detected event, false negative, FN. Any interictal, non-periictal window with no detection, true negative, TN.
Event detection versus sample by sample. They don't just classify each second or each short window on its own. They do event detection in 5-minute blocks or a chosen window size, looking for consecutive positives in the subwindows. Then they ask, does this 5-minute detected event overlap with a periictal label? If yes, true positive, TP. If no, false positive, FP, also called a false alarm. If there is a periictal segment with no overlapping detected event, greater, false negative, any interictal, non-periictal window with no detection, true negative, TN.
extracting the data for this paper, you can see how noisy it is. This is our intervals in milliseconds for P33. Yes, so they vary quite a bit. We extracted 700 megabytes from 850 megabytes of the original data. Okay, so in the extracted data, we now have the CSV, the NPy. Yeah, so what's happening there? Are they exercising or something? These are our intervals for the ECG. The 600,000 samples. The intervals are in milliseconds. Yeah, obviously this P1 train and P1 test are different subjects. You have to be absolutely careful with that. Then we have the process seizure data. Which we can run next. Okay, we still have an error of that. It's extracting data. Where's the presenter lady? Ah, in another tab.
Three, event detection versus sample by sample. They don't just classify each second or each short window on its own. They do event detection in
Event detection versus sample by sample. They don't just classify each second or each short window on its own. They do event detection in 5-minute blocks or a chosen window size, looking for consecutive positives in the sub-windows. Then they ask, does this 5-min detected event overlap with a periictal label? If yes, true positive, TP. If no, false positive, FP, also called a false alarm. If there is a periictal segment with no overlapping detected event, that's false negative, FN. Any interictal non-periictal window with no detection, true negative, TN. False alarms versus false positives versus false negatives. False alarm generally means you flagged a seizure when none actually occurred. In the paper's terminology, that is exactly a false positive, FP event detection window that does not overlap with any periictal label. False negative, FN, means there was a real seizure, but you missed it. Concretely, if no 5-minute detection windows overlap with that seizure's periictal interval, it is a missed seizure, an FN. True positive, TP, means the algorithm flagged an event, one of those 5-minute detections, and it overlaps in time with the clinically labeled periictal window.
Okay, what do you think is happening in these images? This is actually data from the study. Can you give a quick overview and go over each image? Tell me what might be the difference between them. We're using 4.5.
False alarms versus false positives versus false negatives. False alarm generally means you flagged a seizure when none actually occurred. In the paper's terminology, that is exactly a false positive, FP, event detection window that does not overlap with any periictal label. False negative, FN, means there was a real seizure, but you missed it. Concretely, if no 5-minute detection windows overlap with that seizure's periictal interval, it is a missed seizure, an FN. True positive, TP, means the algorithm flagged an event, one of those 5-minute detections, and it overlaps in time with the clinically labeled periictal window. General overview of the plots. These plots show RR intervals over extended periods. The RR interval is the time, in milliseconds, between consecutive heartbeats, R peaks in the ECG, and it inversely relates to heart rate. Shorter RR intervals, faster heart rate, e.g., activity or stress. Longer RR intervals, slower heart rate, e.g., sleep or relaxation. In these images, x-axis, sample index, time progression, typically spanning multiple hours or even days. Y-axis, RR interval duration in milliseconds. Image 1, P15 test RR.png. Pattern observed. Clear cyclical variations, showing repeated patterns of increase and decrease in RR intervals, likely sleep-wake or activity-rest cycles. RR intervals range mostly between 500 to 1100 milliseconds, indicating natural physiological variability. Possible interpretation. The clear rhythm suggests strong circadian variation, likely reflecting periods of rest, higher RR intervals, slower heart rate, and activity. Lower RR intervals, higher heart rate. The regularity might indicate high-quality ECG data without substantial artifacts.
Understand, how does the regularity indicates a high quality ECG data?
Image 2, P14 train RR.png. Pattern observed. Greater overall variability. Intervals are mostly lower, around 400 to 900 milliseconds, indicating generally higher heart rate. Frequent rapid drops and spikes are visible, possibly reflecting episodes of increased activity, stress, autonomic instability, or even seizures. Possible interpretation. Likely more artifacts or irregular activity than the first plot. Frequent sharp spikes might represent signal artifacts or genuine physiological events, e.g., rapid transient changes from seizures or arrhythmias. The shorter RR intervals overall suggest a higher baseline heart rate or more sympathetic activation.
I think you might be reading too much into these images, into this data. there are lots of limitations with it. It seems to be very noisy as well. And there are no details about the actual ECG, yeah, except the peak interval, but yeah, it might be a big problem, isn't it? Because we're essentially trying to diagnose something crucial, like epileptic seizures, using this very simplistic metric. I mean, just diagnosing ECG abnormalities alone, so a heart condition would require more data than that. So let alone when we are using it indirectly to identify an abnormality of the brain.
Image 3. P16 Train RR PNG. Pattern observed. Prominent cyclical patterns similar to Image 1, with RR intervals mostly between 500 to 1200 milliseconds. Well-defined oscillatory nature indicating regular shifts between rest, higher RR, and activity, lower RR. Possible interpretation. Similar to P15, this individual shows strong circadian rhythmicity, likely reflecting normal daily routines, active day versus restful night. The variability appears physiological without obvious prolonged artifacts.
Yeah, ideally the seizures will be labeled on this chart somehow. And also we might need an estimate of what the whole time scale is. Can we derive it from the chart itself? Can you explain what you see in this image as well? It's similar to, well, same format as the previous three, but different patient.
The different patterns observed highlight why seizure detection via RR intervals is challenging. Regular cycles, like in P15 and P16, may generate fewer false alarms. Irregular, noisy patterns, like in P14, could lead to increased false positives due to normal daily variations or signal artifacts. Effective seizure detection algorithms must handle both clear rhythmic data and noisy, irregular signals. The different patterns observed highlight why seizure detection via RR intervals is challenging. Regular cycles, like in P15 and P16, may generate fewer false alarms. Irregular, noisy patterns, like in P14, could lead to increased false positives due to normal daily variations or signal artifacts. Effective seizure detection algorithms must handle both clear rhythmic data and noisy, irregular signals. Regularity versus ECG signal quality. Regularity in RR intervals does not automatically imply high-quality ECG. Regularity refers to the rhythm and pattern in the heart rate, RR intervals. A regular rhythm could simply mean that the person has stable, predictable physiological rhythms, like sleep-wake cycles, regular daily activities, etc. Signal quality refers specifically to how clearly and accurately the ECG is recorded, independent of physiological rhythm. Good signal quality means clear R-wave peaks, few missing or extra detected beats, minimal noise or artifacts, e.g. electrode issues, motion artifacts, electrical interference. Thus, one could have a highly irregular RR interval sequence due to real physiology, e.g. stress, exercise, seizures, with excellent ECG signal quality. Or conversely, a very regular RR sequence could come from an ECG that is poor quality, but where the noise happens to be periodic or consistent.
Why did I initially say regularity implied good ECG quality? Why did I initially say regularity implied good ECG quality?
Why did I initially say regularity implied good ECG quality? That was an oversimplification.
Why did I initially say regularity implied good ECG quality?
Why did I initially say regularity implied good ECG quality?
What is it ignoring the instruction?
Why did I initially say regularity implied good ECG quality? That was an oversimplification. What I meant was clear rhythmic patterns often indicate stable physiological conditions, making it easier to separate genuine heart rate changes, e.g., seizures, from everyday fluctuations. If an RR interval sequence has sharp, random spikes or very abrupt, unnatural jumps, that can sometimes indicate ECG recording issues, signal artifacts, poor electrode contact. Physiological irregularities, real cardiac arrhythmias, seizures, autonomic disturbances. But regularity itself does not directly tell you about the ECG recording quality. A regular rhythm could still have noisy or unclear ECG signals, and a very irregular rhythm could still be captured cleanly. Why did I initially say regularity implied good ECG quality? Why did I initially say regularity?
Why did I initially say regularity implied good ECG quality? That was an oversimplification. What I meant was clear rhythmic patterns often indicate stable physiological conditions, making it easier to separate genuine heart rate changes, e.g., seizures, from everyday fluctuations. If an RR interval sequence has sharp random spikes or very abrupt, unnatural jumps, that can sometimes indicate ECG recording issues, signal artifacts, poor electrode contact. Physiological irregularities, real cardiac arrhythmias, seizures, autonomic disturbances. But regularity itself does not directly tell you about the ECG recording quality. A regular rhythm could still have noisy or unclear ECG signals, and a very irregular rhythm could still be captured cleanly.
Okay, so it seemed to have extracted, now we have 3 different Python files. It seemed to have extracted the data correctly. Now it's in CSV and image files. Now should we be using that extracted data folder instead of the original folder as downloaded?
Yes, once you've successfully extracted the data, you should definitely use the extracted data folder instead of the original downloaded files. The extracted data has several advantages. Compatibility: the extracted CSV and NPY files will work with any version of Python and Pandas without dependency issues. Simplicity: no need to deal with pickle compatibility problems anymore. Portability: the extracted data can be easily shared or used on different systems. Visualization: you already have PNG images for quick visual inspection. Here's what I recommend. First, run the extract_data.py script to extract all RR interval data. Bash python extract_data.py. This script is specifically optimized for extracting RR intervals and should be more successful than the main process_seizure_data.py file. Then, create a new script that works with the extracted data instead of the original pickle files. Analyze_extracted_data.py. Import OS.
Yeah, there's a couple of things. First of all, the summary statistics don't seem to be correct. We need to double check that. But also, can we make sure from the original data set, can you just answer in the chat, are we actually extracting the times of the seizures? We want to be able to display them on the same chart of where the RR intervals are presented.
Yes, your code is correctly extracting the seizure times from the original dataset. From the console output I can see seizure underscore times, class list, length 17. First item 1,529,917,950,086.7766. 1,529,917,966,100.
Know what's reading the code. 17 seizures were detected in patient patient 1. So if it's extracting okay, there's some misunderstanding. There is a misunderstanding. The patient 1 in test and train, they are different patients, are they? The patient 1 in test and train folder are different patients, are they? I don't think this model can actually analyze images. Well, that's why we used the other one. Okay, we have the tree, all the files for the project. Yeah, we're currently using Claude 3.7 Sonnet thinking model, even though we probably don't need the thinking, even though it's always handy to do more thinking than less thinking. Not sure. Anyhow, we have the paper text. We already have 3 Python codes. Extracting data worked well. We lost that tree into file. Yeah, I could try different splits of the data. The data is split in a weird way, and then we're having a problem that the patients' names are the same. I think the bot they got confused because it's actually assuming patient 1 in test folder is same as patient 1 in train folder, which I don't think they are. Hey, can you check the original paper text in this regard?
What indicates ECG signal quality? To properly judge ECG signal quality, you need to look at raw ECG waveform, not just RR intervals, missing beats or extra beats, sudden implausible changes, noise artifacts, high-frequency noise, sudden drops, or impossible physiological values. RR intervals alone are a processed output and can mask or exaggerate signal quality issues. It's incorrect to directly infer ECG signal quality from RR regularity alone. What indicates ECG signal quality? To properly judge ECG signal quality, you need to look at raw ECG waveform, not just RR intervals, missing beats or extra beats, sudden implausible changes, noise/artifacts, high-frequency noise, sudden drops, or impossible physiological values. RR intervals alone are a processed output and can mask or exaggerate signal quality issues. It's incorrect to directly infer ECG signal quality from RR regularity alone. Corrected explanation for your images. Regular cyclical RR intervals, P15 and P16, suggest stable physiological rhythms. Irregular RR intervals, P14 suggest more varied activity, physiological irregularities, possibly seizures, or signal quality issues, artifacts. However, without looking at the underlying raw ECG waveform itself, one cannot conclude signal quality with certainty. Regularity alone does not prove high-quality ECG data.
Yeah, should we continue? I don't know, which voice do you prefer? What's your favorite voice? Okay, major limitations. Yeah, RR intervals are very simplified. Yeah, very limited. Yeah, can we actually use the paper text file to actually update the processing of the data? I'm pretty sure, not 100%, that the P1 in the test folder and P1 in train folder are different subjects. So we have to be careful with that. But yeah, essentially we want to extract the data from these binary pickle files. Who calls a file a pickle? So we seem to be able to do that pretty well. But then we need to make sure we are extracting for each patient. There is a study time pickle, seizure time pickle, and the RR intervals. I suspect we are currently only looking at the RR intervals. Well, anyhow, we need to make sure we extract the seizure times, and potentially when we plot anything, we want to show where the seizure was on the same chart, say in red color. And we have Sonnet Thinking, GPT 4.5 that we just talked to, and I can't be bothered reading all that, so yeah, we'll use one of those text-to-speech. It is ignoring my instructions.
Major limitations and issues with RR interval data for seizure detection. 1. RR intervals are a very simplified representation. RR intervals simply indicate timing between heartbeats, giving only a narrow physiological viewpoint. No direct insight into underlying ECG waveforms. No morphology, shape of ECG waves, example P wave, QRS complex, T wave. No clear identification of ECG-specific abnormalities or cardiac arrhythmias, which might distinguish seizures from normal variations more effectively. ECG alone is already limited, even with full ECG. Diagnosing even pure cardiac abnormalities, arrhythmias, ischemia, etc. requires ECG alone is already limited, even with full ECG. Diagnosing even pure cardiac abnormalities, arrhythmias, ischemia, etc. requires detailed ECG morphology analysis, not just RR intervals. Using RR intervals alone is even more limited, as this method discards crucial cardiac electrical details.
Yeah, now it's not ignoring. So Alloy can do it. I don't know what the stars there mean.
ECG alone is already limited, even with full ECG. Diagnosing even pure cardiac abnormalities, ECG alone is already limited, even with full ECG. Diagnosing even pure cardiac abnormalities.
ECG alone is already limited.
ECG alone is already limited, even with full ECG.
It's just ignoring instructions for whatever reason.
ECG alone is already limited, even with full ECG, diagnosing even pure cardiac abnormalities. ECG alone is already limited, even with full ECG, diagnosing even pure cardiac abnormalities, arrhythmias, ischemia, etc., requires detailed ECG morphology analysis, not just RR intervals. Using ECG alone is already limited. ECG alone is already limited, even with full ECG. Diagnosing even pure cardiac abnormalities, arrhythmias, ischemia, etc., requires detailed ECG morphology analysis, not just RR intervals. Using RR intervals alone is even more limited, as this method discards crucial cardiac electrical details. Noise and artifact issues. RR intervals measured from ambulatory ECG are very susceptible to noise from patient movement, physical activity, muscle artifacts, poor electrode contact, dry skin, sweating, electrode shifts, electrical interference from electronic devices nearby. This can lead to falsely identified beats, missed beats, and incorrect intervals, causing erroneous detections, false positives, and false negatives.
Much better. We are plotting the data from the study. Yeah, we have pretty much all we need. Let's assume it is correct. So we have the red labels for the seizures, and now the authors are claiming that we can detect seizures based on RR ECG intervals. So those are intervals between peaks of ECG, so essentially your heart rate. So this is essentially your heart rate variability, and they say that based on that alone, you can do a seizure detection. Yeah. So this is the natural variability that you have during the day, I would imagine. And saying that you can make a seizure detection out of it is a bit of a stretch, I would think. What do you think? Yeah, we extracted the seizure times. From those pickle files. Who uses or who calls a file a pickle as a pickle? It's just asking for trouble, isn't it? Calling a file a pickle. Analysis results. PE1 train plot. Yeah, that's the problem. It's calling. It's getting mixed up with the files. But that's okay. Yeah, we should essentially pull. I don't know why they split the data that way. Yes, well, you will have a lot of noise in there.
The seizures, if labeled, would appear as transient disruptions in RR intervals, likely periods of significantly decreased RR intervals, increased heart rate, or abrupt variability shifts. Without explicit annotations, vertical lines or shaded areas indicating seizure events, it's impossible to visually identify seizures confidently from the RR intervals alone. Important note: RR intervals alone typically can't reliably pinpoint seizures visually, as similar fluctuations naturally occur with daily activities, stress, or physical movements. Estimating the time scale, can we derive the total duration from the plot? Yes, approximately, if we assume a realistic average heart rate. Step-by-step estimation. Count of total RR intervals, samples, approximately 650,000 intervals on x-axis. Average RR interval, visual estimate, approximately 750 milliseconds, typical resting average interval. Then, total duration, seconds, approximately 650,000 samples, times 0.75 seconds equals 487,500 seconds. 500 seconds, total duration, seconds, approximately 650,000 samples times 0.75 seconds equals 487,500 seconds. Convert this to hours. 487,500 seconds, approximately 135.4 hours. Approximately 135.4 hours equals 5.6 days, based on an average RR interval of 750 milliseconds. Real duration depends on actual average RR interval.
Anyway, it's roughly 5.5 days. It's based on the average RR interval of 750.
RR intervals alone.
RR intervals alone can't conclusively identify seizures visually, don't provide direct information about ECG morphology or brain activity, are susceptible to artifacts, spikes, drops. Conclusion: visual inspection gives a rough idea of activity, rest cycles, and artifacts, but seizures can't reliably be visually labeled without clear EEG video annotations.
Okay, so we have this image that has seizures indicated with red lines and heart rate variability. Can you make an estimate of how long this data is? Can you try and count how many seizures there were? And more importantly, can you tell me how would you go about determining if you can detect a seizure looking at the RR intervals alone? Let's do this with multiple models. Actually confirm from the paper itself how many seizures did patient 1. Yeah, it's a bit confusing because you have multiple patient ones. Oof. $342 false positives. Patient 5 had more than 1,000. Patient 17 had more false positives than true negatives. Is it 10 red lines? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, that's definitely more than 10. It's more like 17, I think, in this case. Yeah, the numbers in the confusion matrix don't look promising today. Anyway, I think we might give this dataset a rest. I don't think you can train a better model looking at this. It's just nonsense. It's nonsense. In the train set, they had 47. The test set, they had 18, so that will be patient 1. That will be patient 1. Can we make sure we are processing data for this patient as well? The true negatives.
Let's modify the code to specifically process the test patient P1's data. Here's a small standalone script that you can run to ensure this patient's data is extracted and properly processed.
Okay, but we won't need the specific script for each patient, would we? Okay, so these numbers do match correctly. We have 6 seizures. So it's essentially found all the seizures correctly in this case. However, it's also found 1600, 1600 seizures that are not actually seizures. No, wait. Uh, Seizure count 17. That's not right. Okay, we have to do it again. That's not correct, is it? Yeah, there might be a discrepancy between the actual data and the confusion matrix. So this is just general terms stuff.
Relating the confusion matrix to the RR intervals plot. The confusion matrix suggests the detection algorithm identified 6 true seizures. Yet, the RR plot visually shows approximately 10 seizure annotations. Why this discrepancy? The confusion matrix summarizes detection performance based on time windows, likely 5-minute windows, as done by Lee et al. Multiple close seizures, 2 or more seizure events within one detection window, may be grouped into fewer events, or detection windows. Alternatively, the detection logic might have grouped multiple short seizures occurring closely into single detected events. This discrepancy would require clarification in the detection pipeline used to produce the confusion matrix, how it defines an event. Understanding the train test split in the seizure ECG dataset based on the research paper and your dataset structure. The specific split, 47 patients in training, 18 in test, was intentionally designed for a pseudo-prospective evaluation framework. Here's why this split is important. Pseudo-prospective evaluation. The authors used a leave one patient out cross-validation within the 47 training patients, then tested on the completely separate 18 patients to simulate how the model would perform in real-world clinical use, preventing data leakage. As mentioned in the paper, this prevented data leakage by ensuring data from the training set did not overlap with the test set and could provide a representation of how the model would perform when applied prospectively. Clinical validation, the holdout test set, 18 patients, serves as an independent validation to confirm that performance observed during cross-validation generalizes to entirely new patients. I recommend maintaining this. I recommend maintaining this split since it aligns with the methodological rigor of the original research. Combining the data sets might compromise the ability to fairly evaluate model generalization, which is crucial for medical applications. If you want to experiment with different approaches, you could, first, reproduce the original methodology with their split. Then try alternative splits as additional experiments. Would you like me to explain more about how to implement the leave one patient out cross-validation approach they used? How to determine if seizures can be detected methodology. To accurately evaluate seizure detection from RR intervals, you would use EEG-confirmed seizures, red lines, as ground truth labels. Segment RR interval data around seizure, periictal windows versus non-seizure periods. Extract HRV features from short intervals. apply machine learning classifier, logistic regression, random forest, etc. Evaluate using confusion matrices, sensitivity, ability to detect true seizures. Specificity, ability to avoid false alarms. Understanding the train-test split in the seizure ECG dataset. From analyzing the code and research paper, I can see why the specific split, 47 patients in training, 18 in holdout test, is methodologically important. Why this split matters. Pseudo-prospective evaluation framework. The researchers intentionally used this split to simulate real-world clinical application. They performed leave one patient out cross-validation within the training set and then verified on completely new patients, preventing data leakage. This approach ensures no overlap between training and test data, which is crucial for accurate assessment of model generalization. Clinical validity. The holdout test set serves as an independent validation, mirroring how the model would perform when deployed on new patients. Performance findings. The paper shows this approach worked reasonably well, better than chance performance in 78% of holdout test patients, average sensitivity of 72%, and specificity of 68% perform. Major limitations: RR intervals alone. Indirect measure: brain event detected via heart. High physiological variability. Normal activities mimic seizure patterns. Artifacts and noise can trigger false positives, FP 342, which is significant. The confusion matrix, 17% false positive rate, indicates that RR intervals alone, although sensitive, produce many false alarms in practice.
Here's a clear, detailed summary suitable for text-to-speech. This analysis shows data from one epilepsy patient, labeled Patient 1, recorded continuously over approximately 6 days. The recording captures RR intervals, which represent the time in milliseconds between successive heartbeats. Typically, shorter RR intervals correspond to higher heart rates, often indicating physical activity or stress, while longer RR intervals correspond to periods of rest or relaxation, such as sleep. In the RR interval plot provided, we see about 10 seizures marked by vertical red lines. These seizures were originally identified and confirmed using EEG and video recordings, which are standard, reliable methods for diagnosing epileptic seizures. The RR intervals visibly fluctuate throughout the recording, reflecting normal physiological variability, such as changes during day and night or periods of physical activity and rest. Additionally, a confusion matrix was presented, summarizing how accurately a machine learning model could detect seizures based solely on the RR interval data. According to this matrix, the model successfully detected all seizures, indicating a sensitivity of 100%. This means that none of the seizures were missed. However, there was a notable issue. The model produced a relatively high number of false alarms, incorrectly identifying about 17% of normal non-seizure periods as seizures. Specifically, out of roughly 2,000 windows analyzed, 342 windows were falsely identified as seizures, while 1,617 were correctly identified as normal. Interestingly, while the RR interval plot visually shows about 10 seizures, the confusion matrix only indicates 6 true positive detections. This discrepancy suggests that multiple seizure events occurring close together might have been combined into fewer detection events during analysis. Clarifying exactly how the detection events were defined would be necessary to fully understand this difference. Overall, the results highlight a critical limitation. While RR intervals alone can detect epileptic seizures with high sensitivity, their high rate of false positives makes them less reliable for clinical use when used alone. These false alarms can be problematic, causing unnecessary anxiety or interventions. Therefore, although RR intervals measured from wearable ECG devices might help in tracking seizures in daily life, they should ideally be complemented with other more direct measurements, such as EEG or additional physiological signals, to reduce false alarms and improve overall accuracy.
You're right, there are some files missing that I referenced but didn't provide. Let me create these necessary files. Prepare_static_data.py. Import OS. Import JSON. Import NumPy as NP. Import matplotlib.pyplot as
yeah, we'll continue this stuff next time. Hopefully we'll have something working on this data set. But yeah, we don't want to spend too much time on it because you still need the EEG. Currently what we're looking at is very messy. So let me know what you think. Don't forget to check the website. And I'll see you next time.